All right, let's dive into two of the absolute titans of the calculus world, the function e to the x and its inverse, the natural log of x. Now, these are not just any old functions. They have these unique, almost magical properties that are totally fundamental to understanding how differentiation works. So, let's get right into it.
So you might be wondering, what actually makes a function a superstar in calculus? Well, it all comes down to having some kind of special property that either solves a really unique problem or just behaves in a way that nothing else does. And believe me, the two functions we're looking at today are perfect examples. They don't just follow the rules of calculus. In a way, they kind of create them.
So in one corner, we've got e to the x. I like to call this one the self-replicator. Why? Because it's its own derivative, which is just a wild concept when you stop and think about it. And in the other corner, we have the natural log of x, the problem solver. This function heroically steps in to fill a huge gap left by one of our most fundamental tools, the power rule. Let's go ahead and meet them one by one.
Okay, first up, let's get into the magic behind our self-replicating superstar, the natural exponential function.
And here it is, the core rule, in all its elegant simplicity. The derivative of e to the x is just e to the x. It is completely unchanged by differentiation. Think about that. It's what we call a fixed point of differentiation, and that is an incredibly powerful idea.
Now, this simple-looking rule has a really profound geometric meaning. It means e to the x is literally the only function out there whose slope at any point is exactly equal to its height at that very same point.
I mean, really try to visualize that for a second. Imagine you're walking along the graph of e to the x. No matter where you decide to stop, the steepness of the curve right under your feet, that's the slope, is perfectly exactly equal to your altitude. That's the y value. It's an absolutely beautiful and unique property in all of mathematics.
Okay, so if e to the x is defined by that perfect self-replication, our second superstar, the natural log, is famous for how it perfectly solves a problem that stumped one of our most trusted tools, the power rule.
And here's its derivative. The derivative of the natural log of x is 1 over x. Again, it looks really simple, but the importance of this little formula is just massive.
So why is this such a huge deal? Well, let's think backwards for a second, to integration. The power rule for integrals works for almost any power of x, except for x to the negative 1. If you try to use the rule on that, you end up trying to divide by 0, which is a mathematical disaster. It's a hole in the rule. Well, the natural log is the function whose derivative is exactly x to the negative 1. It plugs that hole perfectly.
Now, of course, these superstars don't just exist on their own. The real power and the kind of problems you're going to see comes when we combine their new derivative rules with the ones you already know, like the product and quotient rules. Let's see how they team up.
Let's start with a classic. We need to find the derivative of y equals x squared times e to the x. As soon as you see two functions of x multiplied together like that, alarm bells should be going off in your head. This is a job for the product rule.
The process is pretty mechanical once you know it. First, we identify our two functions. Let's call f x squared, which means its derivative, f prime, is 2x. We'll call g e to the x, and its derivative, g prime, is just e to the x. Now we just have to plug those four pieces into the product rule formula, f prime g plus f g prime.
Okay, so plugging them in gives us 2x times e to the x, plus x squared times e to the x. Now, we could leave it like that, but we always want to simplify, right? You can see both terms have a common factor of x times e to the x. When we pull that out, we're left with our clean, simplified answer. Y prime equals x e to the x times the quantity 2 plus x.
All right, one down. Let's tackle our second superstar. This time we need to differentiate y equals the natural log of x divided by x. And that division is a dead giveaway that this is a clear case for the quotient rule.
So let's use that classic mnemonic, low d high minus high d low all over low squared. First, we identify our parts. Our high function, the numerator, is the natural log of x, so its derivative, d high, is 1 over x. Our low function, the denominator, is just x, so its derivative, d low, is 1. Now we just have to plug these four pieces right into the formula. So, when we apply the formula, the first part, low d high, gives us x times 1 over x, which simplifies beautifully to just 1. I love when that happens. The second part is high d low, which is the natural log of x times 1. And that's all over our low function squared, which is just x squared, and there it is. Our final answer is 1 minus the natural log of x, all divided by x squared. So, we've seen our superstars in action. Now, let's just boil this all down to the absolute essential things you need to take away for your own practice.
Okay, here's the bottom line. 4 key things. 1. The derivative of e to the x is e to the x. Memorize it. 2. The derivative of the natural log of x is 1 over x. Lock that in too. 3. Remember, these rules don't live on an island. They team up with the product, quotient, and chain rules all the time. And 4. You absolutely have to get comfortable with these 2 derivatives. I promise you, they are going to show up everywhere in higher-level math and science.
So I'll just leave you with a little food for thought. We've spent all this time on the fact that e to the x is its own derivative. So if you think about the inverse process, integration, what do you think the integral of e to the x is? And what does that imply about the nature of things like population growth or radioactive decay or, well, the very fabric of calculus itself? Pretty amazing stuff to think about.